Welcome to this explainer. Today, we are diving into a technology that completely threw out the traditional rulebook of software complexity, and in doing so became the undeniable language of the modern internet. We're talking, of course, about Go, or Golang. You see, three legendary engineers backed by Google dared to ask a pretty massive question. What if we built a language that was faster than Java, cleaner than Python, and practically eliminated all the bloated, frustrating complexity of C++? Well, the result is a language so elegantly simple it almost feels like cheating. Yet it's so incredibly powerful that it's literally running the largest systems on the internet right now.
Okay, let's jump straight into our roadmap. We're going to break this down into 5 parts. First, the nightmare at Google scale. Second, stripping away C++ complexity. Third, the smart runtime miracle. Fourth, ruling the cloud era. And finally, patience and the AI future.
All right, part 1. The nightmare at Google scale. To really understand why Go even exists, we have to travel back to the mid-2000s at Google. Picture thousands of engineers all working together in one massive repository, trying to build the future of the web, but they are completely bottlenecked. They're using bloated legacy languages that are just breaking down under the sheer scale of the operation. And honestly, this number tells the whole story: 45. It took 45 minutes, sometimes even more, just to test a single code change. I mean, imagine the massive hit to developer productivity. The whole "my code is compiling coffee break" excuse? Yeah, that had become a painful, literal running joke. This was a deeply frustrating, very real pain point that demanded a completely new kind of tool.
The roadblocks with legacy tools were staring them right in the face. On one hand, you had C++, where builds took absolutely forever, and trying to do multi-core programming was a total threading nightmare. On the other hand, you had Java eating up memory like crazy, and Python, which was just simply too slow for heavy, intense systems work. So this is exactly why computing legends Robert Griesemer, Rob Pike, and Ken Thompson, guys who literally helped pioneer Unix and the B language, decided they had to step in and create something completely new from absolute scratch.
Moving on to part 2. Stripping away C++ complexity.
For the Go team, removing features was actually their ultimate superpower. They framed the creation of Go not as a chance to bolt on cool new tools, but as a radical intervention to pull away from C++ complexity. And this quote, it's just incredible. Ken Thompson, who is an absolute titan of computer science, tried reading the proposed C++ 11 standard, the C++ 0x spec, and he literally gave up. The sheer complexity had become so unbearable that it convinced him they needed a completely fresh start. I mean, think about it. If one of the greatest engineers in history finds a language specification too complex to read, the industry clearly has a massive problem on its hand.
And this brilliantly illustrates how they achieved that fresh start. They embraced radical minimalism. Just look at the keyword count across these different languages. Go slashed its vocabulary down to just 25 keywords. Compare that to well over 60 in C++. The creators basically wanted a language that was incredibly easy to read and simple enough that it wasn't constantly picking a fight with the programmer. So the crucial takeaway here is that they treated subtraction as innovation. They stripped the language down to the absolute bare minimum needed to build massive systems. No inheritance hierarchies, no function overloading, no exceptions, and initially, not even generics. Every single feature had to aggressively justify its existence. If a feature didn't actively help thousands of engineers working in the same massive code base, it got the axe. It really proves that true engineering magic often lies in stripping away complexity, rather than just endlessly adding to it.
Let's get into part 3, the smart runtime miracle.
Okay, so we understand the minimalist syntax now, but how do you actually build the thing? Creating a brand new language presents a classic chicken and egg problem, right? How do you compile a language that doesn't technically exist yet? Well, the team used a brilliant method called bootstrapping. First, they wrote a crude compiler in C. Then, they used that C compiler to compile a new version of the compiler that was written in Go itself. Once that worked, they tossed the C version in the trash. And it's worth noting, they didn't start entirely from zero. They cleverly borrowed the incredibly lean, fast compiler architecture from the Plan 9 operating system, which gave Go a massive head start.
Most programming languages force you into a pretty stark architectural trade-off. You either compile straight to native code, like C++, which is lightning fast but highly complex, or you use a virtual machine, like Java, which is super flexible but definitely slower. Go decided to forge a third path. It compiles straight down to raw assembly for maximum speed, but that code links directly to a highly sophisticated smart runtime. This runtime automatically handles the heavy lifting, things like network I/O and garbage collection, completely behind the scenes.
Now, to solve Google's massive multi-core processor headaches, the team brought in Tony Hoare's brilliant concept of communicating sequential processes, or CSP. Instead of dealing with the chaotic, hair-pulling nightmare of sharing memory between traditional threads, Go programs act more like a series of pipes. They pass data through things called channels between lightweight Go routines. The famous mantra here is, do not communicate by sharing memory, instead share memory by communicating. This single decision made concurrency a first-class citizen right out of the box.
And to put that into perspective, just look at this memory footprint. A traditional Java thread takes up about 2 megabytes of memory. A Go routine? It takes just 2 kilobytes of stack space. That is a game changer. Because of this incredibly lightweight footprint, you can literally spawn millions of Go routines concurrently on modern hardware, and the system won't even break a sweat. At the time, that was practically heretical for a systems language, but it worked flawlessly.
Which brings us to part 4, ruling the cloud era.
So let's recap. We have a fast, minimalist, highly concurrent language. This specific technical architecture perfectly positioned Go to absolutely dominate modern cloud infrastructure. And this timeline traces that explosive shift. Go kind of grew quietly after being open-sourced in 2009. But then, 2013 happened. Docker launched, and it was built entirely in Go. Boom, the containerization revolution exploded. Exactly 1 year later, Google launched Kubernetes, also written in Go. This was the definitive 1-2 punch. Docker and Kubernetes acted as these massive catalysts, driving Go's skyrocketing adoption and cementing it at the absolute center of the entire cloud computing revolution.
But why exactly did the architects of the cloud choose Go? Honestly, it wasn't because of flashy features. It was purely practical. Fast compilation, low memory usage, built-in concurrency. But perhaps most importantly, it generates static binaries. That means you can write code on your Mac, compile it into a single file, and it will run perfectly on a Linux server without you ever having to worry about complex, nightmare dependency chains. In the real world, these technical specs translate directly into lightning-fast deployments, rock-solid reliability, and massive cost savings for cloud companies.
And finally, part 5, patience in the AI future.
Behind all of this cloud dominance is a story of incredible, almost stubborn discipline over the long haul. This number, 13, perfectly represents that discipline. 13 years. That is how long the Go team waited to introduce generics to the language. While other developer communities were practically screaming for the feature, the creators simply refused to rush it. They patiently waited all the way until 2022, with Go 1.18, to finally implement generics in a way that fit their minimalist philosophy, without dragging in all that C++-style complexity. It's just an incredible testament to their steadfast commitment to keeping things simple.
And you know what? That discipline has paid off remarkably well today. While Python tends to get all the glory and the headlines in AI research, look at what Go, represented here by its remarkably kawaii blue gopher mascot, is actually doing behind the scenes. 41% of Go developers in AI are building the API endpoints, and 37% are building the data pipelines. Go is quietly providing the hyper-efficient, rock-solid back-end infrastructure that is actually powering modern AI systems in production today.
So this brings us to a crucial thought to leave you with today. From a frustrated hallway complaint at Google to the literal backbone of global cloud computing, Go proved that less truly can be more. As software engineering enters this wild new era of fragmented AI tools and endless complexity, you really have to ask yourself, will your next tool practically solve your problems, or are you just going to end up fighting your compiler again? Thank you so much for joining me for this explainer, and I hope it changes how you look at the tools you build with.